Hello students, I am Electrostatic. Today we are going to discuss about electrostatics. So electrostatics. So it is a branch of physics which deals with the study of electric field, electric potential, electric forces due to static charge. Okay, static charge means the charge which is at rest. Okay, so we can say it is a branch of physics which deals with the study of electric force, electric field, electric fields, electric potential, due to static charge. Due to static charge, that means charge at rest. Charge at rest. Static means it is stationary, which is at rest. Okay. So now, what do you mean by charge? What do you mean by charge? Right. So, as we have got here, it is a branch of physics which deals with the study of electric forces, fields, electric potentials due to static charge. Static means the charge at rest, right? So, what do you mean by charge? So, you have already got the idea of charge in class 9, I think, if I am not wrong. So, there are two kinds of charges. One is positive, another is negative, right? So we used to write this positive and negative to represent the opposite nature of charges. Okay, so positive charge and negative charge, this represents opposite nature of the charges. Okay, now you see, we know matters are made of particles, and the basic particle, the basic unit, building block of matter is called atom. Those things you have studied in class 9, right? So in an atom, we know in an atom, in the nucleus, it consists neutrons, protons and electrons are revolving around the nucleus, right? And electrons are negatively charged, neutrons are neutral, but protons are positively charged, right? So when the atom is neutral, then let us consider, let us take an example of neutral atom. So if it is a neutral atom, then if there are 10 electrons, then the number of protons should be also 10. That means same number of positive charge and negative charge must be in the atom. Okay, so there are 10 electrons, suppose, like this. There are many cells, let us assume that, and total electrons, suppose 10 here in this atom. So we can say there are 10 negative charges, and 10 positive charges for 10 protons, right? If we add additional electron from outside, then this will appear as one negative. This atom will appear as one negative, because when there are already 10 electrons and 10 protons, that means 10 negative and 10 positive, right? It is balanced. 10 negative, 10 positive, it is neutral now. So when you will add extra electron, extra negative charge, then net charge will be when it will become negative 11 negative charges and 10 positive charges, the net charge will be -1, right? So then this will appear as negatively charged. And when if you remove one electron, from this atom, then the number of negative charges will be decreased. So -9, suppose negative charges now 9 and 10 positive charges, so net charge is now 1 positive, then this atom will appear as 1 positive, right? So when you remove electron, it will appear as positively charged, because electron is negatively charged. One negative charge is removed, then positive charge will be one more than the negative charge, right? When you add electrons from outside, then it will appear as negatively charged. So hope you know these things, right? So now you see, let us discuss discuss the properties of charge, right? Additivity. Additivity of charge. Suppose we need suppose we need to find the total charge enclosed by a body, or total charge in a body. Okay. So now you see, suppose different charges, in different regions of this body is distributed. So here you see we have 1 coulomb charge here, 2 coulomb charge here, and we have 3 coulomb charges here. So coulomb is the SI unit of charge. You have already got in class 10, I think, right? So how to find the total charge in this body? Just we need to find the algebraic sum of these charges. 1 plus 2 plus 3, that will be 6, right? 6 coulomb charges is there, net charge 6 coulomb, right? So next property is conservation of charge. Conservation of charge. Now here you see from additivity of charge, according to this property, net charge in a body is equal to algebraic sum of the charges in different regions of the body. Okay. And conservation of charge. So remember, net charge in a body, in an isolated system, is always conserved. Is always conserved. Is always conserved. Right. That means, suppose we have two charged bodies, right? Charge on this is suppose 3 coulomb, and charge on this body is suppose 5 coulomb, and these are in isolated system. That means we are not adding any charges from outside. Okay, so transfer of charges taking place between these two bodies only. Due to the transfer of charges, maybe there may be transfer of electrons, flow of electrons, or okay, or you can say flow of holes. So let us assume, just simply say, if transfer of charges is taking place between these two bodies. Suppose after after transfer of charges from this body to that one, the charge of this body becomes, suppose, 1 coulomb, and charge of this, suppose, 7 coulomb. So here in the first case, total charge 3 plus 5, that is 8 coulomb, and here after the transfer of charges between these two in the isolated system, then also 1 plus 7, that is equal to 8 coulomb. So net charge is always conserved. Okay, so that is the idea of conservation of charges, right? Now you see quantization of charge. Quantization of charge. Now the charge in any body or object is always integral multiple of elementary charge E means charge of electron. That means, you see, charge on a body is suppose capital Q, then it can be written as N into E. So E is the charge of electron, which is equal to 1.6 into 10 to the power minus 19 coulomb. This is the charge of one electron approximately, right? So here N is positive integer. Right. So that means this charge in a body can be expressed as 2 times of E, 3 times of E, 4 times of E. Okay, so you cannot get half of E, 1/3 of E, right, like it. Okay, we do have charge smaller than this. Okay, this is the smallest charge which can independently exist. Though we have charges smaller to this, but they do not exist independently, right? They do not exist independently, right? This is the smallest charge, that's why it is called elementary charge, which can exist independently, right? So these things are clear to you. Now let me clean the board. Now we know when you bring two like charges close to each other, they will repel each other, right? the force of repulsion is electrostatic force between these two charges, right? When you bring two negative charges, then also there will be force of repulsion, okay? And if you bring two unlike charges close to each other, then they will attract each other, right? Then now in this case, now electrostatic force is attractive. So in these two cases, repulsive, and in this case attractive. Now you see how to calculate this force between these charged particles. We can calculate this force using Coulomb's law, right? Using Coulomb's law. Coulomb's law, right? Suppose this is a positive charge Q1, and there is another charge Q2. This is also positive, suppose, and distance between them is suppose small r, right? Then they will repel each other, right? The electrostatic force between these two charges is directly proportional to Q1 into Q2, and inversely proportional to the square of the distance between them. And combining these two, we can write F varies as Q1 Q2 by R square. And in order to equalize, we need a constant, that is suppose K, which is known as electrostatic force constant, Q1 Q2 by R square. And if you keep these two charges in air or free space, then, or in vacuum, then the value of K is 9 into 10 to the power 9 Newton meter square per Coulomb square, right? So this is for free space. Okay, depending upon the medium in which these two are kept, this value will vary. Okay, this will be different for different mediums, right? So K is nothing but 1 by 4 pi epsilon naught for free space. Here epsilon naught is permittivity of free space, right? So instead of free space, these two are kept in medium, certain medium, whose relative permittivity is suppose ER. ER is the suppose relative permittivity of the medium. Then value of K will be given by 1 by 4 pi epsilon naught into ER. So for free space, the value of ER is equal to 1. That is why we used to write only K is equal to 1 by 4 pi epsilon naught. Now you see, what is permittivity? So if these two charges are in a medium, so it will work against the force of interaction between these two, right? Okay, if the permittivity of the medium increases, then this repulsion force or attraction force between the charged particle decreases. Okay, if the value of epsilon r increases, then this force between them decreases. Okay, so I hope you have understood this concept. So now you see, value of epsilon naught, that means permittivity of free space, is 8.854 into 10 to the power minus 12, and its SI unit is the multiplicative inverse of this unit. coulomb square per Newton per meter square, right? Okay, and this is, so instead of K you can write this one also. So this is nothing but this is scalar form of Coulomb's law. Scalar form of Coulomb's law. Coulomb's law, right? This is the scalar form of Coulomb's law. Now you must be thinking, if this is the scalar form, then what is the vector form, right? If I am not wrong. So let us discuss the vector form of Coulomb's law, right? So let me clean this board first. Now you see, let us consider Q1. This is a positive charge, positively charged particle Q1. This is positively charged, positive charge. Let's say positive charge. There is another positive charge Q2, another positive charge Q2, and they are in this Cartesian system X, Y, and this is the origin O, right? And with respect to this origin, its position vector of Q1, position vector of Q1 is suppose R1, and position vector of Q2 is suppose R2, right? And let us consider that displacement from Q1 to Q2, displacement from Q2 to Q1 in this direction, displacement in this direction towards Q1, let it be suppose R12, and displacement towards Q2, let it be R21, towards Q2, let it be R21, right? We know displacement is also a vector quantity. It must have magnitude as well as direction, right? So now you see, as these two are like charges, there must be the force of electrostatic force between them must be repulsive. So that's why this Q2 will repel Q1 towards this direction, and Q1 will repel Q2 to this direction, right? And the force along this direction, that means the force experienced by the charge Q1 because of Q2, let it be suppose F12, and the force experienced by Q2 due to Q1, let it be suppose F21, right? So here you see R1 is the position vector of Q1 with respect to the origin O. R2 is the position vector of Q2 with respect to O. Then F12 is force on Q1 due to Q2, and F21 is the force on Q2 due to Q1. Okay, now you see how to calculate the force F12, right? Let us calculate F12. So according to Coulomb's law, that must be equal to, you can write K into, or you can write 1 by 4 pi epsilon naught Q1 into Q2. So here displacement towards F12 is R12, so we can write here magnitude of R12 square, then R12 unit vector of R12, right? So as you have already got the idea of vectors in class 11, so I have considered that you know these things, unit vector, and you have the basics ideas of vectors. So unit vector, suppose you have a vector, this is a vector A. How to calculate its unit vector A cap? That is vector A divided by its magnitude, right? Magnitude of a vector can be written as like this, giving the modulus sign, or if you don't write the arrow sign, then without using the modulus, if you write this, then also it represents magnitude. Both are same, right? So hope you have understood this. Now you see, let us consider this triangle, this one, right? That is, this is suppose R1 vector, this is the R1 vector, right? And this is the R2 vector. In this direction it is the R2 vector, right? So now let us take R12. This vector is R12. Now let us apply the triangular law of vector addition. Now you see, according to the triangular law of vector addition, suppose you have three vectors which are the sides of a triangle, suppose, right? Then if these two vectors are in the same order, then the third side of this triangle, which is in opposite order, that will give the resultant of the vector addition of these two vectors, right? That means these two are in the same order. R2 vector and R12 are in the same order, right? And this is in the opposite order. R1 vector is in opposite order. So we can write that R2 vector plus R12 vector is equal to vector R1, right? So from here we can write clearly that R12 vector is equal to R1 minus R2 vector, right? R1 minus R2 vector. Similarly, if you calculate the unit vector of R12, then how to calculate that? R12 vector by its magnitude R12 simply, right? So here you see R12 is equal to this one, R1 vector minus R2 vector, and here magnitude of R12 will be the magnitude of R1 vector minus R2 vector. You can write this one like this as well, okay? Now you see, replace this unit vector, this is unit vector, right? Replace this by this result, and this R12 also can be replaced by R1 minus R2, right? So we can write 4 pi epsilon naught. So here you see, this can be written this way also. The vector magnitude can be written using the modulus sign, right? So R12 is this, right? So mod of R1 vector minus R2 vector. This gives the magnitude, and its square, whole square is there. So here it is Q1, Q2, right? Then this R12 is replaced by this value. Let me clean this. Now this will be, this R12 will be replaced by this value, right? That means R1 minus R2 vector divided by mod of R1 vector minus R2 vector, right? So hope you have understood this. Now if you multiply these two, then you will get 1 by 4 pi epsilon naught Q1 Q2 by mod of R1 vector minus R2 vector whole cube, right? Then into R1 vector minus R2 vector. So this is the vector form of Coulomb's law. Vector form of Coulomb's law. Vector form of Coulomb's law. Similarly, we can calculate F21 as well. So here you see F1 and F2. let me clean these things. F21, if F12 is this, then F21 will be is equal to 1 by 4 epsilon naught Q1 Q2 by R21, magnitude of R21 whole square into vector unit vector of R21. Right. Now you see it can be written this way also. If you change this R21 by R12, right? If you change this R21 by R12, then we will get minus here, because the direction of these two vectors are opposite, right? So there will be a minus sign by epsilon naught. So it can be changed by R12 now. R12 vector square minus R12, right? We can write this way. So this is nothing but F12, right? So minus F12. So these two forces are equal but opposite in sign, right? Equal but opposite in direction, not sign. Equal in magnitude but opposite in direction. So here you see, if F12 is equal to this, here we are getting R1 vector minus R2 vector whole cube, and here R1 minus R2. So in case of F21, if you find F21, then you will get 1 by 4 pi epsilon naught Q1 Q2 by, instead of R1 minus R2, you have to write R2 minus R1 vector modulus here whole cube into R2 vector minus R1 vector, right? So that is what F21. So hope you have understood. This is the Coulomb's law, vector form of Coulomb's law, right? So now let us discuss another topic. Electric field. An electric field intensity now you see why I am writing these two, because you see, let me explain. Electric field intensity at a point when you will read different books written by different authors, in some books this word may not be there, right? It also can be written as electric field. Instead of writing intensity, they may write only electric field at a point. When it is said that electric field at a point or at somewhere, then always remember they are talking about electric field intensity. That means how strong the field is, right? So generally, if we say only electric field, as you have studied in class 10, so if we have a bar magnet, then around it there must be a magnetic field. Similarly, if we have a charge here, charge particle, right, due to charge particle and which is at rest, we will have electric field, right? You see, so electric field is the region within which if you place another charge here within that region, this is suppose capital Q, if you bring another charge in this region, then this charge will exert force on this, right? And out of this region, beyond this region, it cannot exert force on this charge, right? So this region is called the electric field of this charge, electric field due to this charge. Okay, now electric field intensity at a point, suppose if you consider a particular point here in this electric field, then the strength of the electric field at this point is the electric field intensity at this point due to this charge. Okay, how to calculate that? Let me show you. And we will discuss electric field lines also. So before going to this topic, let me explain about electric field lines as well. Now you see, in order to study, as we imagine magnetic field lines with outside the magnet emerge from north, merge at south, right? You have already studied this in class 10, right? Emerge from north, merge at south, and inside the magnet the direction is south to north. So these are closed curve, but it will be a little bit different in case of electric field lines. So as to study the behavior of magnetic field, we used to assume this magnetic field lines. Similarly, to study the electric field, we also assume some imaginary lines, right? So those are like this. For a single positive charge, they are radially outward. The direction of the field lines radially outward. Okay, and in case of negative charge, electric field lines are radially inward. Okay, radially inward, right? And if you have two charges, this is positive, this is negative, then radially outward from the positive charge and inward to the negative charge, right? Coming out of the positive, going into the negative, positive to negative. So these lines of force are not closed curve. Why? You see, in case of magnetic field lines, here you can see these lines of magnetic field lines emerge from north, merge at south. Then inside the magnet again it is going from south to north. That is why it is closed. Here it is, you see, from positive charge only electric field lines coming out and going into the negative charge, right? Okay, this is going in one direction only, that is going out, right? So no field lines coming from negative to positive, so that it can complete this loop, right? So that's why these are not closed curve. Now you see, if you draw a tangent, suppose this is a positive charge and this is the negative charge, and this is the electric field line. Suppose this is another electric field lines, this is another electric field line. Let us suppose this is a point. If you draw a tangent here, right, and if you give the arrowhead towards the negative, then this direction will give you the direction of, this is the direction of electric field. Let me write E field at this point P. This point is suppose P, at P, right? This tangent will give the direction of electric field at that point. Okay, like the magnetic field lines, as you have studied it in class 10, they do not intersect. Similarly, electric field lines also do not intersect. Remember that those things. Okay, So now let us discuss about electric field intensity at a point. Let me write it on the top. Right. Electric field intensity, or simply electric field, at a point due to a charge. Now you see, we have a charge Q here. Right. We have a charge Q here. Let me take this is capital Q, suppose capital Q. This charge is capital Q at this point. Right. Let us bring another charge small q, which is placed at the point P. This is the point P, and this charge is placed at the origin O, suppose. Right. Now you see, this point is suppose P. If this charge can have electric field, then this small q charge also can have electric field. It actually must have electric field, right? But we have assumed that its electric field is very weak. It's too weak, so that it doesn't disturb the electric field of this charge. Okay, let us assume that way. Now, this is the distance between them, that is r, suppose, right? Now you see, according to Coulomb's law, the force acting on this small q charge due to capital Q, according to Coulomb's law, we will get by Coulomb's law. We will get K capital Q, or instead of K you can write 1/4 epsilon naught capital Q small q by r square. This is the magnitude of the electrostatic force between these two. Right. Now, if you want to find the electric field at this point, then you must calculate the force acting on per coulomb charge. If you have brought here q coulomb charge, then what will be the amount of force exerted on 1 coulomb charge? That will be the electric field, magnitude of electric field at this point. That means, suppose F force is being exerted on the small q charge, right? So on small q charge, F force is being exerted, then on 1 coulomb charge, so F by q force will be exerted, right? And this will be the electric field. So in order to find the force per coulomb charge, let us divide this equation by q, both sides. Let us divide the both sides by q. F divided by q. If you divide this one by small q, q will be cancel each other. Then only capital Q left by r square. This is nothing but electric field. This is what? Electric field. This is electric field at P due to capital Q, right? If the unit vector along this direction is suppose r cap, then in vector form this electric field E vector can be written as 1 by 4 pi epsilon naught capital Q by r square r cap. This is in vector form, right? Now you see, I have already told you that this charge is very small, so that its electric field doesn't disturb the electric field due to the capital Q. That's why this E can be written as limit Q tends to 0. That means Q is very small, F by small q, right? So hope this thing is clear to you, right? So what is the SI unit of electric field? Now electric field force by charge. So SI unit of force is Newton and that of charge is Coulomb. So SI unit of electric field, SI unit of electric field is Newton per Coulomb, right? Newton per Coulomb. So hope you have understood these things. So pause the video and note it down. So let me clean the board. Okay. Now let us discuss about electric flux. Electric flux, right? So what do you mean by electric flux? Suppose this is a surface. This is a surface. And it is kept in an electric field, and the direction of electric field is suppose perpendicular to this surface, right? This is electric field and the area of this surface is S, and electric field lines are passing through this area S, right? Then flux will be given by, flux through this surface will be given by E into S, right? Right? Here you see, electric flux can be defined as the total number of electric field lines passing through a surface normally is called electric flux. Electric flux through that surface. Through the surface. Right? So which is given by phi is equal to E into S, right? Now you see, let me take this case now. Just let me clear this. Now this is the surface, suppose. And these are electric field lines, right? So which are not perpendicular to this surface now. And the area vector means, suppose if you have taken this surface, this is the surface, then area vector to this surface will be normally outward from this face, and for this face this will be again normally outward, right? So that is area vector, right? So here suppose this is the surface, its area vector will be directed in this direction so that it is perpendicular to the surface. This is the suppose area vector, and angle between the area vector and the electric field is suppose theta. Right. Now you see this electric field vector, this is as area vector and this is theta. This is electric field vector. It can be resolved into two components, right? So here you see one component will be along this, that will be E cos theta, because angle between these two is theta, and another component will be normal to this component, right? That will be E sin theta, right? How to resolve a vector into two components you have already studied in class 11, right? So I hope that you have understood that, right? So now you see the component which is along the area vector, right? E cos theta, E cos theta. Now to calculate the flux through this surface, we will take this component only, because you see from the definition, the total number of electric field lines passing through a surface normally. Here you will see this electric field is not perpendicular to this surface, not normal to the surface. They are not passing through this surface normally. So that's why we have to take that component which is passing normally through the surface, which is E cos theta, right? E cos theta. So therefore flux through this surface phi will be E cos theta into S, which can be written as E S cos theta, and E S cos theta means E vector dot S vector phi. So you know dot product of two vectors A and B, suppose the dot product can be written as AB cos theta. So now if we have ES cos theta, then we can write E vector dot S vector, right? Very simple. Hope you have understood this. Now you see, so when the flux through this surface will be maximum and when it will be minimum, maximum and minimum, right? Now you see the maximum value of cos theta is 1, right? Cos theta, when cos theta will be 1, when theta is equal to 0. That means theta means angle between the area vector and the electric field. So that means if this is the surface and this is the area vector S, and electric field lines are parallel to this surface, area vector, parallel to the area vector, not the surface, parallel to the area vector, right? That means perpendicular to the surface and parallel to the area vector. Then theta will be equal to 0 and cos theta, that means cos 0 degree, will be equal to 1. So then phi, so when E vector parallel to S vector, that means theta is equal to 0, then you will get phi is equal to E S cos 0 degree, which is equal to E into S, which is the maximum value, and when electric field is perpendicular to the area vector, not perpendicular to the surface. Perpendicular to the area vector means this is the surface and this is the area vector S, suppose, and perpendicular to this area vector means parallel to the surface, right? Like this. This is the direction of electric field. In this case, theta is equal to, suppose theta will be here 90 degree. So theta will be 90 degree. So cos 90 we know 0, right? Cos 90 is 0. Then here in this case theta is equal to 90. So phi will be Es cos 90 degree, that is equal to Es into 0, that is equal to 0. That is minimum. So this is minimum flux. So hope you have understood this. Now let us discuss Gauss theorem. Now let us discuss about Gauss theorem. Gauss theorem. So according to this theorem, the total flux through a closed surface is equal to the 1 by epsilon naught times of the charge enclosed by that closed surface, right? Suppose we have a closed surface here. This is a closed surface, and it encloses a charge, suppose Q. Then flux through this entire surface will be 1 by epsilon naught times of Q. That means Q by epsilon naught, right? That is what Gauss theorem says, right? So we can write the total flux through a through a closed surface of area S is equal to 1 by epsilon naught. Epsilon naught, you know that permittivity of free space, right? Times of the charge, suppose Q, enclosed by the surface, right? That means electric flux, you can say phi, which is also written as integration E dot ds is equal to Q by epsilon naught, right? So this is the mathematical expression of Gauss law. Okay. Now let us prove this Gauss theorem. How to prove this theorem? So in order to prove this theorem, suppose I have charge here, positive Q charge, right, which is at point O, right? So around it, let us have a closed surface, spherical surface, let us say Gaussian surface. Gaussian surface means such a surface at all the point or at each point on that surface, the electric field is same, right? Electric field is same. Okay. So now you see this Gaussian surface enclosed a charge Q, right? And its radius be suppose R. Let us take its radius be R, so that if you take a point here P, then its position vector with respect to O is suppose R, given by R vector, right? Given by R vector. Let me assume that way. Okay. Now let us take a very small area element. Now you see this is positive charge. The electric field should be radially outward in this direction. This will be the direction of the electric field, right? Okay. Now let us take the unit vector along this R vector. We suppose R cap. Okay. And if you assume a very small element, area element ds, where the p lies, very small area element, suppose ds, then the area vector, the unit vector of the along this area vector, this will be the area vector, this will be the ds vector, and along this let be the n cap be the unit vector along the area vector, right? So hope you have got these things up to this point. So this is the very small area element. Let us consider very small area element. Now you see, let me clean this statement. Now you see, flux through the small area element, the small area element ds is given by E dot ds vector, right? E dot ds vector is equal to so let me represent it by d phi is equal to E dot ds vector, and direction is along n cap. Direction is along n cap. N cap is the unit vector. N cap is the unit vector normal to the surface ds, normal to the surface element ds. I am not talking about ds vector. This is the surface element ds. That means I am talking about this surface area, small surface area element. Area vector is ds vector, and when you say ds, just let me write like this only. This is the small area element ds, and the unit vector along this area element is suppose n cap, right? Which is normal to the surface ds. So now you see, electric field, this is suppose equation number 1. Now electric field at P due to Q positive charge. So we have already discussed how to find the electric field at a point due to a given charge. That is, E vector is equal to 1 by 4 pi epsilon naught. We have discussed that this is a capital Q. So we have discussed the electric field at point P due to this capital Q charge. We have got this E vector is equal to capital Q by, if the distance between these 2 points is suppose r, right, then r square. If you write in vector form, then we used to write r cap, right? Now we don't have capital Q here, we have small q here, so we will replace this capital Q by small q, right? Hope this thing is clear to you, right? This is suppose equation number 2. Now you see, in order to find the electric flux through the entire surface, this is the flux through very small element ds, then electric flux through the entire surface will be given by phi is equal to integration of d phi. If you integrate over this entire surface, then you will get this, right? So as we are taking Gaussian surface, so E is constant, it can be written outside the integral, right? Integration ds here n cap. So we can write this, right? D phi is equal to this one, so we have used that one here. Okay, so now you see E vector is equal to this. If you use equation number 2 here, then you will get. So here we have got this one from 1, right? From equation number 1, and from 2 you can put the value of E here. Let's put this one here. 4 pi epsilon naught Q by R square. We have R cap here. Let us multiply this one with n cap, right? Then integration ds vector R cap dot n cap, right? So now you see this R cap is the unit vector along this radius, and this is the unit vector along this area vector. N cap is the unit vector along the area vector, and both are in the same direction. This is the R vector, R cap, this is the n cap, in the same direction. So dot product of these two, R cap dot n cap. Here you see these two are unit vector, so their magnitude will be 1, again 1, magnitude of it will be 1, then cos, here both are directed in the same direction, so cos 0 degree, so cos 0 is 1, so we will get 1. So dot product of these two will becomes 1. So 1 by 4 pi epsilon naught Q by R square, and integration of ds. If you integrate this surface, then you will get the whole surface of this Gaussian surface. So I hope you have got the concept of integration and differentiation in mathematics, right? So if you integrate this over the whole surface, then what you will get, this is a sphere, so area of a sphere is 4 pi r square, right? 4 pi r square, and r cap dot n cap, that's become 1, as I have shown here. So here you can see 4 pi cancel, r square cancel. We have only q by epsilon naught, q by epsilon naught. This is the Gauss law. Flux through a surface is 1 by epsilon naught times of q. Q by epsilon naught means epsilon 1 by epsilon naught times of q, right? So this is the Gauss law. So hope you have understood this. So this is what Gauss law or Gauss theorem is proved. So hope you have understood. So thank you for watching. See you in the next class.